Perfect. Awesome. Thanks, Matt. And I don't know, Gabe, do you want to, like, just for my own purposes, like I'm sure like your entire cohort knows who you are, but oh, okay. Well, I'm glad I could be here for that. Well, we're being recorded. I guess the screen is being recorded, but awesome. You know what I like about that, Gabe? Most of the stuff that we're going to be doing in statistical reasoning is if then questions. So this is you're going to crush this. You're going to have it under control. So awesome. All right. Well, glad everybody could make it. I've been talking with some of you individually about some questions about where we're at in terms of materials and things along those lines. Again, come in, touch base, talk with me if things come up. Want you to feel very, very comfortable with this material because again, unfortunately, it's all cumulative, right? So if I don't understand one thing, I'm going to be in trouble as we move to the next thing because these statistical concepts don't go away. They keep building on one another. So use one another, use me as a resource, use Matt as a resource. We've got this first problem set coming up, not this Friday, but the following Friday is when it will be due. So you still got a lot of time with that, but do go through, get an early start on that. It sounds like people have gone through, pulled that up, starting to look at that a little bit. Uh, Again, just for clarification, it'll just be one, you only have one document that you turn in for the whole group. How you go through and decide on division of labor and things like that is sort of up to you. Again, the one thing I would reiterate is that because it's important that we're going to have a midterm and a final, which is just you going through and doing things, making sure that however you decide to chop things up, that you're working together and that everybody understands different pieces and parts of that. But for this, it's mostly just I don't think there's any calculations on this. It's more conceptual questions and stuff like that. So just type something up. In terms of your written stuff, um, none of this is going to be something where I'm expecting pages and pages of prose. I'm not going to tell you that you not to do that because I want you to feel comfortable in whatever response that you give me, but don't feel pressure that you need the 7 pages. Oftentimes we'll sort of this type of work and throughout the whole semester if you got a good handle on what you're on what the concept is, you can kind of almost always say that pretty succinctly. Sometimes what happens in an effort to try and cover all your bases, and if you just start saying words, what you'll do is spoil answers, and then you get stuff wrong for that. So it's trying to find that balance, and certainly sometimes people will give me answers, but I think you know what you're talking about, but I need a little bit more in order to be able to sort of get it versus people feeling pressure to write pages and pages and pages, which is not what I'm looking for on anything. So keep that in mind, and if you have questions, come talk with me. I'm happy to give you guidance about like, oh, you can sort of be a little more succinct with this or what have you. So cool. Any questions on any of that stuff? Just email it to us. Yeah, I don't know. Canvas is just what you'll do is you'll send that document to what we'll do is you'll send the document electronically to Matt and I both. So to CC us both so that we just have a record of that. And then what I like you to do is just print out a hard copy and put that in Matt's box. And that way Matt can go through and physically go through and sort of write comments, and then he'll kick it over to me. I'll go through and sort of do the final scoring and comments and things along those lines. So we'll have the electronic copy and then the physical copy. Now, when we get into set 2, there'll be like some hand calculations and stuff like that. And I'm going to have you draw on some pictures and things along those lines. And so that'll be that you'll have like sort of other stuff that you can just kind of staple together, but we'll cross that bridge when we get there. Cool. All right. Any other questions? Cool. All right. So we finished off last time. I'm recording and this is all working. Okay. Finished off last time with talking about sampling error. Okay. Olivia, there we go. Olivia, tell me what well, it's on the describe to me sort of what sampling error is. Exactly. Is sampling error yeah. No, you did a beautiful job. You didn't just read it. That's awesome. That's awesome. You did that's a great I really like what you're up to. Olivia, does sampling error mean that I have an unrepresentative or a biased sample? No, right? When am I not going to have sampling error? Never, right? So this is the thing. I think this is where people get sort of turned around on this because sampling error sounds like a bad thing, right? And it's not great. We can do things to minimize our sampling error, but anytime we have a discrepancy between our population parameter and our statistic, that's our sampling error, right? Now, sometimes we're going to have lots of sampling error. Sometimes we're hopefully going to have not too much sampling error, but sampling error is just a fact of life. It's like COVID. It's here and it's around. We're just going to have to deal with it the best that we can. There are things we can do to minimize it, but it's something that's always going to be there. It doesn't necessarily mean it's a bad thing, right? Or that you've done something wrong. We went through and talked about factors that are going to impact sampling error. Sample sizes, our sample gets bigger, our sampling error gets smaller. We're getting a more representative sample of the population we're trying to get, right? So our sampling error is going to shrink with sample size, with sample selection. If we have random samples, that's going to reduce our sampling error because we're, in theory, going to get a better representative sample of everybody. And then the measurement tool, right? The better, more precise tools that we have, the better the estimates we're going to get, and it's going to reduce our sampling error. These are all methodological issues that should be on your mind as you're thinking about building projects, looking and evaluating research to try and think about to what extent is the sample that I've got actually targeting and getting at sort of whatever construct it is I'm trying to measure. Okay. Any questions about sampling error is just such a critical component of sort of thinking about conceptually what's going on. People feeling comfortable with sampling error and what this is about. Okay, awesome. So want to touch base real quickly, thinking about theoretical constructs. Talking about construct as any characteristic that can be observed, cannot be directly observed, but useful for describing, explaining information. Haley, can you give me an example of a construct? Perceptions. Perceptions is a wonderful. Can you give me another construct? Attitudes, right? Basically, you can just yell words at me. They're all constructs, right? Things like height is a construct if we get sort of down sort of close enough to it, right? Height is sort of constructs are the things that we are trying to go through. These are the in theory things that we have decided are sort of useful in describing some aspect of experience. This is what we're trying to measure with our analyses, right? Our operational definitions, these are the rules by which we've decided to measure some sort of observable behavior or characteristic that we're deciding represents a hypothetical construct, right? So so my research is in post-traumatic stress disorder, right? I can't see PTSD, right? I can't measure it directly. I can ask people questions about some experiences they've had, and then I can say, yes, these things are consistent with this construct that we've identified as post-traumatic stress disorder, but that measurement is going to depend on how I've operationalized post-traumatic stress disorder. For a lot of our research, I might say that PTSD is operationalized as scores on the PCL. PCL is a common measure of post-traumatic stress disorder. It's a self-report measure, and I can say PTSD as defined, as operationalized as this, right? But if I'm doing work with, say, kids or some experimental types of things, right, where I'm looking at doing experimental work with aggression or things along those lines, right? I might say that aggression is defined in my study as the amount of punishing stimuli I deliver to a supposed opponent within the context of this paradigm, right? Is that actual aggression? Is that a good measure of aggression? I don't know. That's worth debating, right? But it's how I've gone through and operationalized this construct. Okay. So the reason just want to go through and talk about these things is that these operationalizations are essential. What we're trying to do is we're conducting analyses on numbers that are imperfect representations of a construct. Okay. Always remember that this is like sort of, we're never actually looking at PTSD or aggression or attitudes or any other thing else directly. What we're doing is we have some measure that we've collected data on. We're saying this data, these scores represent this construct, but we always have to remember that our methods are imperfect, our analyses are imperfect, right? And so this starts to drive our interpretations, right? I would never say that with 100% certainty that sort of this thing impacts PTSD, because what I've done is I've measured sort of what my predictor is with error, with an imperfect measurement, and I'm looking at PTSD as measured through it, which is an imperfect construct measured with an imperfect measure, right? I think the tendency is within, as an undergrad, you go through and you read stuff and be like, oh, well, this is published research. And so, yeah, there's an effect between X and Y. Maybe. It all depends on the methodology. Do we think that their measures of their construct are good and believable and credible? Are they measured reliably and validly? Do I agree with their operationalization of whatever it is that they're trying to measure, right? Because I might think I've got a pretty good measure of X. You might disagree. And if that's the case, then we start to sort of be a little less certain about some of our interpretations. Okay. Also, this is important for statistics. I can't fix bad methodology. Okay. If you've measured something using a really questionable measure, there's not a fix for that. There's not a correction. I can't sort of do some numbers on it and fix that. That's a methodological thing, right? So always wanting to be careful and thinking about when we're designing our own research, being very concerned about our methods, right? And our measurements. If I've got a measure that's got a ton of error in it, what does that do to my statistical power? It goes down a lot, right? It goes down a ton. Because if I've got just so much sort of random static in there, it's going to be hard for me to get a signal. So this is why when we talk about like, oh, it's important to have valid measures, reliable measures, things along those lines, this is why it's important, because it's going to help us at the end be able to identify our constructs, or sort of identify the relations that we're interested in. And so wanting to think about this, not just it's something to do just because we should be doing it, it's also helping clarify our analyses. Okay. People comfortable with this? Okay. Also important when we're analyzing or evaluating research in this class, in other classes for theses, comps, and things along those lines. Just because someone measured something or a measure is named something, it doesn't mean that measure actually captures that thing. We hope it does, but that's up for debate. That's up for critical evaluation, right? So thinking about the methodology when we're going through and interpreting effects differences and things like that, to say what can we say, what are reasonable interpretations we can pull from this, and what can't we. Okay. All right, getting into sort of the measurement of our constructs, want to think about level of measurement. This is something that we get into in a lot of like undergrad stat courses, but it starts to become important because level of measurement starts to become really important in terms of identifying what types of analyses do we use, right? Who here is nervous about like deciding, sort of choosing what analyses to apply to your data? Yeah. Like, I don't know, like, what do I do? How would I go through and do this? If you measure what your inputs are and your outputs are, what are your predictors? What are your outputs? What's the level of measurement of those inputs and those outputs? If you can answer those two questions, that's going to start to narrow down your options very, very quickly, right? So always important to be thinking about how we're measuring our variables. Overall, we can talk about variables as continuous and discrete. Continuous variables, in theory, are values that can take on any number, right? there's an infinite number of values that for a that of a continuous variable can take a discrete variable. These are going to be, by definition, categorical variables, right? That can take on discrete values. All right. We can break this down even a little bit farther. For our discrete variables, we can talk about nominal and ordinal levels of measurement. Can someone help me out? What's a nominal? What's nominal measurement? Yeah, Mandy. Yeah. Yeah. Can you give me some examples? Gender, political party, things along those lines, right? I can't rank order these. There's no order to these. They just are. They're just categories, right? Experimental condition, right? I don't know. I've got condition A, condition B, and a control condition. It's not like one is sort of incrementally higher than another. They're just things that are, right? What about an ordinal variable? What makes an ordinal variable ordinal? Go ahead, Gabe. Almost close. We do know, and we can say that one's bigger than one, or one's lower than two. Yeah. Sort of in terms of I can have. I know that in general, 3 is bigger than 2, and 5 is bigger than 3. But is for me the difference between a 3 and a 4 the same as the difference between a 4 and a 5? Things along those lines. Nope. We're just sort of rank ordering things. Yeah, Kate, did you have a? Yep, we could think about freshman, sophomore. It depends on how we want to think about it, right? Like if we're talking about years of education, then yes, that would sort of be ordinal. But we could take that same category and construe it differently so that it is probably more consistent with a nominal variable. And so this is beautiful because this is where we have to really start thinking about what are we trying to measure? What's the construct? And then what is the physical sort of manifestation of that we have? And sort of how does that all fit together? No, that's excellent. Did someone else have their? Okay. Yeah. Yeah. Perfect. Right. So we've got an order and we can all generally roughly agree about the order, but sort of the space between those is not the same. And I can't get like second and a half place, right? I can't have 2.5 kids because that's not a real thing, right? So thinking about ordinal stuff, the thing that's important to remember is that for almost all of our like self-report scales, what type of, even if we're pretending it's continuous, what type of level of measurement are we getting on self-report scales? Ordinal data, right? My level of sort of negative affect right now is not necessarily Allison is not necessarily the same as Allison's level. Like I said, Allison might have a 5, I might have a 6, but really, in fact, Allison might objectively have more negative affect than me, right? And so we start to get into really sticky stuff that starts to, one, have some conceptual implications, but then two, also have some implications for analyses and how we go through and deal with this. Okay, our interval and our ratio scales, these are true continuous variables, right? These are things like uh, temperature in Fahrenheit, I guess, for interval, right? The difference between 22 and 23 degrees is the same thing as 50 and 51 degrees. It's the same thing. It's just that 0 point doesn't have a true zero value. 0 degrees Fahrenheit means it's the absence of temperature, right? It just means it's just a random point on the scale. Our ratio variables, same thing. It's just where that 0 has a true meaning. This is really not a huge distinction with the types of stuff that we normally do, but just want to know the difference between those two. Okay. And so the reason we want to be very clear sort of at the conceptual level, and sort of this is the other thing too, right? We can think about my concept or my construct may be continuous, but how I measure it might not be continuous, right? So again, breaking this apart, thinking carefully about what's my construct, how have I measured it, what's the level of measurement, and if I know those things, it's going to be critical to helping me choose how I might best go about and looking at relations or associations between variables. Feeling comfortable with this? And Hal does a really nice job of kind of working through this. And this is the stuff that can get surprisingly tricky in terms of thinking about like sort of what this actually is as you're working through stuff. Yeah, Gabe. Yeah. Yep. Same thing, like an IQ test, right? An IQ test is you sort of have the full range. But a 0 doesn't mean that you have no IQ, right? Like if you're scoring there, that would be, I guess technically you could, but like sort of that there's something's gone wrong then if that's happened, right? And so, yeah, sort of trying to wait through and say like sort of what is this and where is this is a good conceptual exercise, and just will make sure that you're strong on your constructs and sort of how all this works together. Okay. Other questions? All right, cool. So switching into central tendency. Okay. If we're talking about measures of central tendency, this is some approach that we're going to use to find what's the single best score that best represents or defines the middle of a distribution. Okay. Again, what we're trying to do is we're trying to find a value that best represents my sample, right? I know this doesn't represent everybody, but like if I had to just give one number, what's the number that best kind of captures the middle part of this entire group? Okay. For our between and within group comparisons, the stuff that we're going to focus on this semester, sort of this measure of central tendency is critical to sort of our approach to running some of these analyses. Okay. Bad news is there's no single best method for determining central tendency. Okay. This is a thing I hope you sort of, I hope that you all can get in. There's no best of anything. There are things that are useful in some circumstances and less useful in other circumstances. Being able to differentiate between these is sort of the main task of good quality applied analyses, to be able to go through and say, all right, in this circumstance, these are the pros, these are of these approaches, and being able to sort that out. Okay. So for this distribution, Mesa, 100. Yeah. All right. Distribution, Mesa. You tried to avoid. Didn't. I'm locked in. 0 is the best. Why? Okay. Anybody else have different thoughts on that? Johnny. -2 or -1. Okay. Why do you think that's the best middle measure? Okay. Okay. Yeah, the mean value is going to be skewed. I'll take exception. I wouldn't say that the majority of the data is the tail. Actually, the minority of data is in the tail. The majority is in the bulk, right? And so when Mesa says 0, that's definitely where the bulk of scores are. But is that the middle? Maybe not, because you've got that tail, that negative skew coming out, right? What about this? What's the best middle value of this, Lindsay? 165. Okay. But again, if we're thinking about if our measure of central tendency is intended to best capture sort of the most how many people are at 165? That actually doesn't represent much of anybody in this sample, right? What might be going on if we look at what we're measuring here? What might be going on in this? What type of distribution do we have, and what might be going on? Exactly, right. So we've got a couple of we got a bimodal distribution. What might be going on with this? Yeah. I mean, like, there's a pretty separated here, right? But almost any time, like, sort of that should be the first thing. If you see a bimodal distribution, the first thing that should enter your mind is like, do we have a couple of different distinct populations within this, right? And so here, identifying a measure of central tendency is really difficult because we've got kind of a modal and a mode value and a secondary mode, but trying to identify one value that's most characteristic of this entire distribution is starts to become difficult, right? So when we're trying to determine which measure of central tendency to use, a couple of things we want to think about: shape of the distribution and the type of data that we're going through and using. Okay, our mean is our most common, probably our most common approach to describing the middle of the center of a distribution. You think about mean in statistical terms, you'll sometimes see this referred to as the first population moment. Moment is a characteristic, right? So of the different ways we can sort of characterize the shape of a distribution, mean is your first population moment, and the mean is just the sum of scores divided by the number of scores. It's just an average, right? Fancy word for average. Population mean, sample mean, scored the exact same way. Okay, we'll see this little sigma. This sigma sign. What does sigma mean? What's that? Sum. Add it all up, right? So if you see who's scared of sigma, does sigma give people anxiety sometimes? Yeah, gives me anxiety sometimes, particularly if it's in a pretty big equation, right? It just means just add up everything after it. Okay, so here we're just adding up all our x values and dividing it by the number of scores in the sample. Same thing for our sample mean here. Okay, we can also calculate a weighted mean. What we're doing here is we're using this to find a weighted average across a couple of different samples. Here, our weighted mean is going to be the sum of all our scores in our first sample, sum of all the scores in our second sample, and we're going to divide that by the number of scores in the first sample divided by the number of scores in the second sample. You need to remember sample means, okay? Why is that not correct? Why is that a trap that we can fall into? What do you think, Gabe? Yeah. Yeah. Exactly, right? If I have the mean age of, if I take the mean age of traditional undergraduates and I take the mean age of non-traditional undergraduates and I just average those two means, do I get the average mean of all, or the average score of all people in a university? Nope, that's going to be way off base, right? Because we've got a whole lot more traditional students than non-traditional students, right? So just remember, our weighted mean is that we can just take the mean of sample one, the mean of sample two, take the average of those two, and get the mean for the full group. Except for when we can. When can we do that? When does that math work out? I think getting there. What do you mean by homogeneous, Lindsay? When they're the same size. If I have two samples that are exactly the same size, then I can just take the average of the means and we'll get the sample mean for the whole thing. But rarely in psychological research are we ever actually using exactly the same size. Sometimes the difference will be trivial, sometimes it won't be. So just if we were running a weighted mean, remember that this is the formula for weighted means, and that we're not just taking the average of samples. Yeah. Yeah. So let's say um, Danielle, I'm wanting to look at the difference between condition A and condition B on some outcome, right? And I want to look at the at the uh, at the overall mean, right? I could calculate it in that way, right? I mean, I could just sort of take everybody's scores. I mean, this is essentially just adding up everybody's scores, dividing by the total number of people in the sample, right? And that will sort of get me there. But sometimes if I'm like looking at two different studies with two different samples and I want to look at the average mean across samples, what I need to do, what this formula does is it takes into account the number of people in each sample. Okay. So if I have one study with 150 people in it, another study with 75 people in it, what I can't just do is take the average of the two means and say that's the overall average across these two studies. I'd have to calculate in the number of people in each one of those. No problem. Good question. Other questions? Cool. Characteristics of the mean. Okay. So the nice thing about the mean, so this is the strength and the weakness of the mean. Strength of the mean is that the mean includes all scores included in the distribution. Everybody gets a say. Okay. There's no value that's left out of the calculation of the mean. So all scores in the sample contribute to the calculation of the mean. So what this means then is if we change a score, it changes the mean. If we add a new score, it changes the mean. Okay. Except for when can we add a new score and it doesn't change the mean? If it equals the mean, then it's sort of right there, right? But in general, and this is a pain, I'll tell you this right now, is because what you'll be doing is you're running a study, so you're running some analyses, and you realize like, yikes, I should have not had this person in there. This person shouldn't be in the sample. And so I go through and kick them out. What has that almost certainly done is change my mean, right? And so then I have to go through and recalculate and things along those lines, right? So pros and cons of mean, but yes, if I change a score, it will almost always change, or it will for certain change the mean. If I add a new score, it will almost always change the mean, unless the new score is exactly identical to the mean, which often can also happen because the mean is a decimal place because it's an average of things, and my score on my measure, whatever, will oftentimes have to be a sort of a whole number, right? So, other thing that we can think about, if I add a constant, subtract a constant, multiplier, divide a constant by every single score in the sample, it's going to change the mean by that value. Okay. Again, this is a basic concept with scaling, right? If I measure something in inches, right, and I have my mean in inches, and then I go through for all my values and I change them to feet by dividing those inches by 12, it's just going to change my average number, or my average in inches. I'll just divide that by 12 and I'm going to get my average in feet, right? And again, if we go through and take a look at the distributions, adding, subtracting, multiplying, or dividing every score in that distribution by a constant doesn't change the shape, right? If I measure something in inches and then I measure something or rescale that to calculate that in feet, it doesn't change the shape of my distribution. It's all the same. Everybody's the same. So taking arithmetic, changing everything by an arithmetic constant of all scores, it doesn't do anything to your distribution. This isn't a transformation. It's just a rescaling. Okay. All right. People comfortable with the mean? What happens with the mean? Okay. So mean is great. And the mean is what the vast majority of our statistics are based on that we'll be using, right? And again, the benefit of the mean is that it takes on, so that all values in the set contribute to the calculation of that mean value, okay? But we also have other options. We have the median, okay? The median, this is just the middle. It's the score in the distribution that splits my entire sample so that 50% falls on one side, 50% falls on the other, okay? So if I've got an odd number of values, I just list all my values from highest to lowest and identify the middle score. Here's what we've got. We've got 15 scores. We've got 7 scores below, 7 scores above. 3 is that middle score, okay? If I've got an uneven number of scores, I can go through and score from highest to lowest, select the middle pair. So if the middle pair is both 15, then the median's 15. If it's sort of one's 14 and one's 15 on both sides, then I sort of maybe take the midpoint of this. So I say the median is 14 and a half. Now the downside is that 14 and a half is an actual value that's in the set, right? So it's not a real value that represents anything, right? But it's a way that you'll commonly see to break down that middle piece, okay? So if we're thinking about distributions and quartile methods and things along those lines, it's your middle point. It's your middle, it's your score that separates half on this side, half on this side, in terms of calculating our median. Mode, this is going to be our score or our category with the greatest frequency, okay? Benefit of the mode is we can use this with any scale of measurement, right? The mode isn't limited by any level of measurement. I can always calculate a mode. Mode is just going to be the score that's the most common in my set, okay? We can have bimodal, multimodal distributions. And here, what you often see is talking about a major mode and minor mode, or a primary mode and secondary modal values and things along those lines. Rarely will you get straight up camel hump distributions where you've got identical modes across, right? But what you would just describe these as bimodal, multimodal, if you've got prominent swells in the distribution here. Okay. Here we go. Yep. Major mode, minor mode, just ways of describing some of these distributions in terms of what's happening. So here we would say in the slide we have a major mode of 4 and a minor mode of 0, right? But there's not really that much difference. It looks like we've got like a 1 score difference between these two. That's the other thing, want to go through and take a look at your scaling and sort of understand how much of a difference that we've actually got with this. Feeling okay with mode? Mode's easy, right? Mode's just, it's like the most in there. Okay. All right. So how do we go through and choose? What do we decide if we're trying to describe our data? What decisions are we making in terms of determining which one of these is the best? Okay. Mean, we really like this. This is generally what we're going to go with. It's generally going to provide, particularly if we've got large samples, a representative value for the set, right? It's hopefully we're going to get something that's kind of semi-normal, and it's going to be something that's kind of there in the middle. Every score in the distribution counts the calculation. What we're going to see is greater stability across replication samples in our mean relative to our median and our mode. Why might we see being more stable than the median and the mode? Say a little bit more about that, Haley. Okay, so it's more representative. You're also capitalizing on aggregation, right? Whereas if I'm looking at a mode, if I've got a nice distributed, like a fairly normal distribution, maybe in one sample, on a continuous variable, maybe in this first sample, my mode is 53, and the other one it's 49, and the other one it's 52. Even those are the differences across these, like functionally you couldn't tell the difference between these. We're just sort of capitalizing on minor variations across these samples, whereas if we were to calculate the mean, it would be very stable across those. Same thing with the median, it's the middle value, right? That's kind of sort of working in, but that can start to jump around. Your median or your mean tends to be more stable as a point estimate across replications. Yeah. Uh-huh. Okay, hold on to that. We're going to get that. Yep. So generally, what we're looking at is the mean. Mean is also a basis of most of our inferential statistics, even when we get into things like regression and things like that, because mean is central to calculating a lot of our variance estimates and things like that. So they're still identified as mean-based statistics, even though we're not doing group comparisons. Okay. Limitations of our mean. Easily influenced by extreme scores. This tends to be less of an issue with psychological science because of the types of constructs that we measure. Abby, give me something that you would measure in your area. ageism, levels of ageism, and how do we measure ageism with this scale, right? So even if I'm the most ageist person in the universe, there's only so high my score can be. I kind of cap out on that, right? Which is typical of the types of things that we study, because we study hypothetical constructs that we can't actually directly observe, so that we have to create measures to observe them, and there's only so high you can get on a measure of a scale. Versus if we're working in something like an area like econ or something like that, right? If I'm measuring something like income, I can have people be multiple standard deviations above everybody else, and that starts to really, like, I just need one Bill Gates or Warren Buffett or someone in my sample to really start throwing things off huge, right? So really, we don't. Or if I'm looking at housing prices, I only need one mansion in my district to start really throwing things off, right? So the types of things that we use, will always be looking at extreme values and thinking about the influence of that. But we're kind of lucky in that, like, a lot of times there's only so far out you can start to stretch things there. But the mean is influenced by extreme scores. We also might see that the value might not actually exist as an observed score. The mean may not be a real score that anybody in the whole sample has. It's still a representative sample or representative value, but it's not. No one in my sample actually has a specific value of the mean. And so wanting to think about, is that a problem based on the application of what I'm wanting to do? And then truly the interpretation of our mean relies on the assumption of at least interval data. Why is this? Dylan, any idea? Why, if I'm going to have a literal interpretation of the mean, why does this depend on interval level data or continuous data? Yeah. What about for ordinal data? Yeah, exactly right. What ends up happening, right? If I'm looking at the average temperature in Laramie in August, which is quite nice, right? What I can do is I can go through and calculate sort of based on records, and I can create an average temperature, and that temperature could be 72.864, and I can just take that into infinity, and that's an actual value that exists in the universe, right? What if I'm trying to take the average number of kids or the average number of houses people have? Those are ordinal scores, right? I can do it. We do it all the time, but 2.5 kids isn't a real thing, right? There's no real score that exists there. Now, oftentimes, like you were saying, like with Likert scores, like I can see they say the average score on the PCL in my sample is a 23.7. 23.7 isn't a real score that someone can score on that, right? And so technically it's not a real value, right? Now we sort of overlook that, and it doesn't cause a big deal in the types of things that we do, but something to be that you should be being careful about and thinking about in terms of level of measurement. And do my scores actually have real meaning to them? Okay. Questions about this? Like, nope, no scratching. You have to answer questions. Median, okay? Median can be preferable in a lot of different cases. Most often, if my data is skewed or has meaningful but extreme values, okay? So if I get Michael Jordan or Jerry Jones or someone in my sample, right? And I'm really interested in sort of making sure that they're in there because they're a relevant person for me to think about, but they're so far out there, they're going to screw up my mean. A median might be a good way to go through and look at the middle value. This is why you'll see home prices. Home prices, it's money. That's a ratio scale. Like I can literally have $0. I have zero wealth, monetary wealth, right? And I could calculate a mean of home values that has an actual real meaning, but it might not be representative if I have properties that are high expensive, right? So what I could do is I could choose a median, right? I still want to recognize that I do have those really expensive properties out there, but I don't want that screwing with my mean, right? Or if I have skewed distributions, right? And this gets to Mesa, uh, sort of your sort of identification back. Oh, well, it's about at this level. And Johnny's like, oh, maybe it's down on this other level. Probably a better representation of the middle of that distribution is somewhere in between. If we have positive and negative skew, this follows a lawful sort of pattern. Your mode is always going to be so the farthest out to one side. Your mean is always going to be the on the other side. Your median is going to be in the middle of those two. Okay. And so often with skewed distributions, what you'll identify the median as the maybe a best metric to go through and characterize the middle of the distribution. Now, not just because like if you have a little bit of skew, you probably don't have to worry about that. But if you start to get more skewed distributions, median is often sort of an attractive option. If I'm looking at scores here, right? What's going to happen if I calculate the mean of that? Going to jack that up a whole bunch, right? Because I also have one person at 10, 4 people at 20, 3 people at 30, one person at 40, and one person at 120. With that sample size, that's going to pull that way out, right? I'm going to get something that's probably way out here, right? And that doesn't represent anything. But if I go through and I take a look at the median, my median is going to be kind of right here, and that's going to give me sort of a better representation of that. Okay. Yeah. Yeah, no, and this is a really excellent question. We're going to talk about this too when we're talking about measures of variability, right? And thinking about talking about why graphical representations can start to be really helpful in sort of looking at, because if you see this, now, is there a lot of variability in this in these scores, Andy? Not really, because most people are just kind of really tightly packed right here. But I've got one person of things, right? Now, this is a situation, large sample, a lot of things, right? In this situation, that score is really messing with stuff. Like we can't use that score the way it is. Now, if this is, I've got, concerned about that. We're still concerned because it's a weird score and I would want to what the hell's going on with the person who scored 120. I would want to go back through my records and make sure that that was a valid observation and not sort of a miskey or something along those lines, right? And we'll talk about that a little bit, but it's going to be less of a problem if I've got a really big sample. But if I've got a small sample with the type of stuff that we sort of work with commonly, then that starts to become a pretty big issue, right? So thinking about this in terms of describing our data, and this is what you're going to be doing a lot with your screening, is talking about like, okay, we went through and found some extreme values. This is what the actual value was. This was a standardized score, so we can start to understand not just, this is why I'm going to encourage you to not talk about things in terms of outliers. Because outliers is like a categorical thing. Either it is or it isn't an outlier, but there's no basis for determining what is an outlier. We start talking about extreme values, right? It's in a value that sort of sets far enough and sort of talking about more a difference in degree than kind. Okay. But this is a pretty extreme sample where this would, you couldn't do much with these data anyway. You don't have enough people, but this would really start to throw things off. Other questions about median? All right. Also, helpful if we're have analyses with censored data. Can someone tell me what censored data is? Anybody know? Yeah. Yeah. What's that now? Oh, That could be censored, but probably sort of not necessarily. But yeah, I've been working on some stuff with trimmed stuff, right? So we're and yes, we will talk about that as censored data, and that I've gone through and trimmed the top and the bottom. Censored data, if I have a top to a scale, right? So if these data here, let's say I'm looking at how many miles a day people drive, right? And I've got this I've binned this into 10 unit increments going from 0 to 9 to 90 to 99. And all of those are sort of things. And then I've got 100 and over, right? Why is this problematic for calculating a mean value? Yeah. Yeah. If this is how I've recorded it, I have no way of knowing how far is this a mile over or 100 miles over, right? I can't calculate a mean, a meaningful value of the mean for this, but I can calculate a median on this, right? And so if we're looking at censored data, and this is the thing, people will do this all the time. It's just like, oh, I'm just going to go through and run a means analysis on them. Like, well, I don't know, particularly if I've got a lot of people up there, right? Starts to become problematic, right? So thinking carefully about level of measurement and how this impacts our statistics and the types of things that we're going to go through and do. Okay. Data involving ordinal scales, right? Technically, a median is a preferred approach to capturing the middle value because with our ordinal data, there is no equal assumption of equal spacing across these. If I go through and I calculate a mean, it assumes that sort of I've got a continuous variable, that there are sort of meaningful differences in the middle. Median doesn't depend on equal or assume equal intervals between values. So technically, if I'm looking at ordinal data, median is technically the preferred way to go about through and identify that, because the median is going to give you an actual sort of value without assuming the assumption like the mean that all values are equally spaced. Okay. Yeah. That is censored. Yeah. So our censored data says that we measure up to a certain point, and then everybody that goes above that, we're grouping them in the same category. Other questions? People see why technically, if we're being sticklers, if we're being rules people, why ordinal or for ordinal data, a median would be the approach of choice. Now we violate this all the time because almost all of our data that we're collecting with self-report measures and things along those lines are going to be, now Lindsay, if you're doing sort of, you're in Kyle's lab, right? Okay, like if you're doing like sort of mass or something along those lines, then you're obviously not. But if you give an eating disorder scale out, right, then you've got an ordinal score, right? Now we treat ordinal data as continuous quite a bit, and we can oftentimes do that without sort of major impacts on our outcome. But if we're going to do it, we should recognize what we're doing and sort of being able to sort of understand sort of what the potential consequences are of that before just treating everything as if it's continuous. Yeah. All right. Other thing to be thinking about is when we go through and we analyze transform data, okay? Transform data, if we're doing group-based comparisons on transform data, these are technically looking at differences in sample medians, okay? Transformation, this is going to change the shape of our distribution, but it's not going to change the order of scores. The person who is, we're looking at here, we've got audit scores. This is an alcohol use disorders, this is an alcohol use measure, right? And we almost always find that this is going to be scaled or skewed, positively skewed, because most people aren't going to have alcohol problems, but some people are, and some people are going to have really extreme alcohol use disorder or difficulties. And so what we'll often see in this area is people looking at transformed scores of this, right? But as soon as we start to transform things, it starts to reduce our interpretation. If you tell me this is tells me this is someone's sort of mass in kilograms, I know what that is. If you log transform that, this is someone's log transformed weight. Now all of a sudden I don't know what that is. I don't have a frame of reference for what that means, right? But it may be something that is useful for going through and doing for statistical purposes. But what we need to do is always remember that what we're reporting on are transform scores, not the actual scores, right? But if I go through and I transform scores, if I look at the median in this distribution of my raw audit scores here, I have a median of 3, right? If I go through and I log transform these scores and look at the distribution, it's changed the shape of the distribution. This is something that looks better for the types of things that we would want to go through in terms of mean-based comparisons and things like that, right? And now my median is 1.1. Can someone have a calculator? Haley, can you take the natural log of 3 and tell me what that is? Yeah, I know. Oh, yeah, you turn if you turn your phone sideways, that should pop open. What did you get? What's that? Really? 0.09. That's are you taking the natural log or the actual log? You're probably taking. Oh yeah, so it's the LN one. Okay, there you go. See, he's trying to screw up my magic show here, right? All right. Yeah, you use a base 10 instead of base C. It's a rookie mistake. No. So yeah, if we take this of 3 and we log transform it, it still ends up being the median. The median value, the middle value, the center value doesn't change, right? The transformation changed the shape of the overall distribution. It is something that's more accommodating to the types of analyses that we might like to run, but it doesn't change the middle value. The mean is going to change, but the median doesn't. It's constant, right? But the problem is when sometimes we always want to think carefully about transformation. We're running analyses to understand something about constructs and relationships between different variables and behaviors. As soon as we go through and we start applying transforms, it changes the interpretation of those, right? And so we always want to make sure if we're implementing transforms that we are then sort of anytime we talk about that, we're talking about differences in a transform variable. But technically what we're doing here with these is looking at changes or differences in median scores across groups as opposed to actual mean values. Okay, so we're still using means-based analyses, but what we're really looking at is differences in medians as opposed to differences in means with this stuff. All right. Questions about median and when median is an option to be thinking about. Last nominal scales, right? If I'm just measuring some categorical thing, median doesn't make any sense because I flop things around and it's sort of my median changes. Mean certainly doesn't make any sense. Nominal scale. So if we're looking at things like ethnicity, sort of major, right? Sort of these types of truly categorical things, mode is really your only option with this. If I have ordinal data, sort of count data, mode can be nice, right? I could calculate median number of children, or I could say modal, right? Like, what's the most common number of children that people have? What's the most common number of rooms in a residence that people might have, right? Mode is nice because mode is really easy to understand. It's the thing that comes up the most often, particularly if we look at a distribution and we have a very clear modal value in there. Mode can be nice. And also thinking about using mode as a supplement to other measures of central tendency. This is if I have something like that is bimodal or something like that. I could say median value is this. However, within this distribution, we have a major mode here and a minor mode here. as a more descriptive way of going through and talking about and describing to people what the shape of an actual distribution might look like. Okay. Right. Questions about mode or any measure of central tendency. I want to go through and switch over into variability. Variability, this is probably one of the most critical concepts to really, really get a handle on in terms of thinking about like what is variability. Like even when you do undergrad statistics, be like, oh yeah, variability is a thing. You talk about variability, but a lot of people don't have a good like conceptual understanding of what that means, what that looks like. As we start getting into applied statistics, this is a concept that's central to everything that we'll be doing, right? So really, really want you to have a good understanding of what variability is, what it entails, what it means when we're talking about variability. Sort of very basic variability just refers to the extent to which scores are spread out or clustered together, right? To what extent are my data spread out from one another? To what extent are they all sort of kind of in the same spot? If I have all of my scores are the same, then I have no variability. If I have no variability, what do I have? Do I have a variable? Nope, I have a constant, right? And that's problematic for analyses. We need some variability, okay? But if my variability is, if I have a lot of variability for some types of analyses, it can be kind of problematic, right? If I'm looking at means-based comparisons, if within my groups, within my conditions, I have a lot of variability in my conditions, then I've got a lot of static in that, right? So, but if I'm looking at correlations and I don't have any variability, then I've got a problem because I'm not going to be able to detect sort of the associations that I'm wanting to detect. So variability, just something that is, it's good in some places, it's not so great in other cases, right? But variability as essence is just talking about to what extent are scores spread out or clustered together, okay? Our different indices of variability are going to describe some distribution in terms of a distance or sort of a distance between scores. Like if I give you a sort of metric of variability, this should help you understand if I were to just pluck randomly random scores out of this distribution, how close together or far apart in units would I expect those variables to be, okay? So thinking about this is a metric of what can I expect across replications, how different should I expect things to jump around, right? If I have low levels of variability in my set, Daniela, and I pull two random scores from that, if I tell you I have low variability in my set, what would you expect from in terms of the relation or the distance between those two randomly selected scores? This should be pretty small. Does it have to be pretty small? Does it have to be pretty small? Oh, no. But so you're exactly right. Yes, I would expect them to be pretty small. Do they have to be small? Could they be quite far apart? Yeah, they could be, right? I could just manage to just by pure chance, right? I draw the smallest score and the highest score in the distribution. Probably not. I would expect in general, if my distribution has sort of not too much variability, I would expect them to be pretty close together. Doesn't have to happen, but if I keep repeatedly grabbing two randomly selected scores, on average, they're going to tend to be pretty close together, right? What about if I have a distribution with a lot of variability? And if I say I got a lot of variability here and I grab two randomly selected scores, what should I expect for those two randomly selected scores? Where should they fall relative to one another? Probably on average, they're going to be farther apart. They don't have to be. I could pull two scores if I've got a big sort of nice normal. Obviously, they're going to kind of be around the middle of that curve, so they might be close together, but there's a lot of opportunity for them to be much farther apart, right? Which gets us into thinking about variability in terms of distance, but we can also think about variability in terms of representation, right? If I've got a distribution that doesn't have a lot of variability, what that's saying is my middle score or any individual score is probably going to be pretty representative of sort of the sample as a whole, okay? So if we think about undergrads on campus and we're thinking about age, is there a lot of variability or not a lot of variability in age for traditional undergraduates on campus. Not a lot. Probably everybody's going to be about in that 18 to 21, 22 range, right? And that's in the grand scheme of age, that's not much. So if I go through and I just grab a random undergraduate off of Prexis and say, hey, you, how old are you? Whatever they tell me is probably going to be pretty representative of the general sort of developmental stage of sort of most people there, okay? But what if I'm sort of walking down the street in sort of New York City and I grab a random person off the street, right? Probably a lot more variability in random people on the street in New York City, right? And so if I go through and I grab one person off of there and say, how old are you? How is that going to be representative of all people on the street on that day? Probably not at all, right? So we can think about with our means-based analyses, right? What we're doing is we take this sample and we calculate a mean and we say, this is our best guess, the most representative value for this condition, this group, this sample, right? But if I have a lot of variability in my sample, am I more or less confident that that individual score is a good representative of everybody in, or not so confident about that? Not so confident, right? But if I've got a condition with very tight variability, so again, let's say you're running something on sort of gamification and people's sort of preferences for like standard old dry, like sort of read the script versus the game thing, right? If I'm looking at liking and I see that everybody's doing pretty good and everybody's definitely liking this, any score I pull is probably going to be pretty close to sort of whatever the mean if there's not a lot of variability there, versus the standard thing if there's a lot of variability. Like I could pull somebody, but and I can say like this is my best guess for about where people should be, but any individual within that set could be kind of all over the place. Okay, clinical people think about treatment outcome stuff, right? We tend to see a lot more variability at the end of treatment than we do at the beginning of treatment in these studies. Because people are coming in at the beginning of treatment, all pretty feeling not great because they're volunteering for treatment. So people in terms of severity are going to be pretty close. Then we get to the end of treatment, lots of variability. Why do we see lots of variability at the end of treatment? They don't work for everybody. Not everybody participates. There's a lot of, we can get all sorts of, this is how much we're going to see in terms of a reduction in terms of people, but there might be a lot of variability in that. That could mean anything from no improvement to tons of improvement, right? So thinking about variability in terms of distance, in terms of the variable or the scores in this set. You're kind of seeing sort of, they're all correct, but they're just different ways of kind of thinking about and conceptualizing variability in ways that are flexible, that start to map onto different sort of aspects of our distributions. Yeah. Yeah. Yeah, exactly. Yep. Yep. So let's say, and we'll get into this when we get into our like t-tests and things like that. Let's say, Mandy, you have condition A and you've got condition B, right? And you randomized people to condition A or condition B and had them go through some sort of experimental manipulation. And you're measuring, what are you measuring? Okay, let's like think about like a measurement. How about this? How about this? Let's say you're measuring anger. Okay, let's because you're really into anger, right? Sure, sure. For the purposes of this example, yes, right. And so what you've got is you have um a manipulation where it's kind of a control, and then like an anger manipulation where you're just trying to tick people off because of something, right? If the only thing that impacts people's anger is this manipulation that you've had them complete, randomized, and that's the only thing that drives anger, what should everybody's anger score be in your experimental group? Yeah, it should be identical. If the only thing that impacts anger is your manipulation, everybody should have the same score. Is everybody going to have the same score? No, they're going to bounce around to some, right? And hopefully in this situation, what we would expect is that anger score would be pretty small, because if it's not, there are lots of other things going in, and that other stuff starts to create static, right? And so I can say the average score on anger, right? But if I've got a lot of variability, what is that? It's because it's something that I haven't accounted for, right? And if there's anything that I haven't accounted for, and specific, can't account for in our model, what do we call that? What is it? By definition, it could be, it could be, it could be lots of different things, right? And it is not necessarily random stuff, right? But it's just things that we haven't accounted for. And by definition, if we haven't accounted for it, then it's error. It's unexplained differences, right? And so this is why we can think about in our means-based analyses, right? If I say, here's the mean of this group and here's the mean of this group, any deviation from that is error. It's stuff that we haven't accounted for, right? And so error in that way. Does that help? Okay. Other questions? People got a good sense for variability? All right. So same thing, central tendency. There's lots of different ways we can think about, lots of different things we can, ways we can conceptualize or measure variability. One of the simplest ways is going to be range. Okay. Range, this is just the distance between the largest and the smallest score in a distribution. Okay. A couple of different ways we can calculate. We can calculate range as the highest score minus the lowest score. That's how SPSS is going to calculate it. You can calculate it as the highest scores minus the lowest score plus 1. Cool. Like, I don't know, like people, like nerds will get in like real big fights about sort of like which one is the right way or the wrong way. I think if that's what you're worried about, you've got a lot of time on your hands, right? It doesn't matter that much, right? So just thinking about sort of the difference between the highest and the lowest score here, okay? Limitations though of our range is that it's going to be determined by our two extreme scores. Nothing else in the middle matters. It's solely determined by your min and your max value. If I've got distributions that have unusually large or small scores, it's going to be misleading, okay? And because it doesn't consider all the scores in our distribution, it's going to be inaccurate a lot of different times, okay? So again, if we go back to this graph here, Johnny, what, if I calculate range and I just report range, what's the range on this going to be? Yeah, give me like a value of 17. So I've got 17 in this distribution. Does that accurately describe what's actually happening in this? Most of my scores are pretty tight. Like everybody's really kind of clustered around here. I just got one that's way out there, right? But if I just report range without any context, that doesn't provide a reasonable description of what's actually happening in this sample. Okay. Some additional range statistics. So we can talk about range as the top and the bottom score. We can also start breaking things into quartiles. Okay. This starts to become sort of some of these talk about these as medium-based statistics. And for those clinical folks who are in Tara's class right now doing some assessment stuff, sort of quartiles and things along those lines start to become sort of more relevant. Some experimental folks, depending on the sort of the area, this can start to come in. But if we think about the first quartile, this is going to be the spot in the distribution that defines the lowest 25%. Okay, literally 25% of scores are going to fall between that first quartile. Your second quartile, this is the center of the distribution. This is your median. This is your 50th percentile, right? Half of your scores fall below this point. Half of your scores fall above it. Third quartile, this is the upper 25. This is the 75th percentile. These are the folks that are scoring higher than 75% of all people in the sample, okay? And then what we can do here is we can calculate our interquartile range. This is going to be the difference between the first and the third quartile. Okay, talk about this as your middle 50. If you take the chop off the bottom 25%, the top 25%, what you've got is the middle 50% of your distribution, and that's going to be your interquartile range. Okay. So here, if we're looking at a nice, clean, normal distribution, here we've got the median or the 50th percentile happening right there in the center. Your first and your third quartile, cutting off the bottom 25%, the top 25%, your interquartile range is the distance between those two. Okay. And this is just a nice way to go through if you've got things. If you have a nice normal distribution, these quartiles correspond to specific probabilities in that distribution, which is nice characteristic. But if we've got really kind of ugly sets that don't really kind of form to a nice distribution, this can be a nice way to go through and think about things, because it's not getting, they're not means-based statistics that are getting pulled out by very, very high or very, very low scores. Okay. So interquartile range is nice, because it's not going to be tossed around by extreme scores like your ranges. Interquartile range is going to just tell you kind of the distance between your 25th percentile and your 75th percentile, right? Where that middle 50% of scores land. But you're also cutting out half of your data, right? The top 25% is gone, the bottom 25% is gone, and you're just getting the middle stuff, right? Which generally for us in psychology, we would say that this is probably not a primary way we would want to go back and go through and do this stuff. But for brought up censored in terms of cut, sort of, who was that? That me? So was that you? What's that? Oh, it was Mandy. Okay. When you're talking about censored data as data that where you have it, and the argument is I don't actually care about sort of the weird people on the top and the weird people on the bottom. I'm just most interested in identifying what people typically do. That's when you'll see people use censored statistics where they go through and not the top 25 and the bottom 25, but maybe like the top 5% of scores. We'll get rid of those, the bottom 5%, and just use sort of that middle. And generally, if you've got scores that are way out on the margins, we're just going to ignore those because they're not representative of the people we're interested in. We're just going to focus on the middle. All right, we're going to get back into these quartiles and the interquartile range when we talk about box plots or box and whisker plots. But does anybody, so people have a decent understanding of kind of what we're capturing here? All right, let's take a break. We'll come back and jump into variance and standard deviation. So yeah, take 10, yeah, come back, be back here by 3:40. I am incapable of keeping things constant and straight in my head. So like, never feel like I'm going to get upset if you're asking me or reminding me about something, because I probably need it. So thank you all in advance. All right. So I'm going to jump into variance and standard deviation. Anybody sort of having people feeling comfortable about the concept of variability in general? Okay, so this is the thing, like a small semantic thing, but it starts to become important to making sure that we're clear in terms of what we're talking about. Variability is any sort of description of distance and things along those lines. Here we're going to talk about variance. Okay, variance and standard deviation. These are very specific statistics calculated in a very way. So just if you're talking about variability in a data set in terms of the spread of scores, talk about the variability. Variance, we're talking about the specific calculation. So just make sure that you're square on that when you're going through and not getting those confused. Easy to do, but it happens sometimes. So just keep an eye on that. Variance, standard deviation, these are going to be our most common indices of variability. Standard deviation, we can loosely interpret standard deviation as So roughly the average distance of any given score from the mean. Okay. So if you have a mean of a distribution and I were to randomly pull a score out of that distribution, my standard deviation is telling me sort of approximately the average distance I would expect any randomly selected score to fall from the mean. Okay. That doesn't mean that every score is going to fall that distance from the mean, because then that wouldn't make any sense, but on average about how far it's going to go. It's not exactly the average. We'll talk about why that is, but roughly speaking, that's what we can, how we can think about your standard deviation. Variance, this is your second population moment or your second population characteristic. Mean being the first, variance being the second, talking about the spread of scores. Your variance is going to be the average squared distance from the mean. This is critical in terms of the calculation of statistics. Variance doesn't have, though, carry as much interpretive value as your standard deviation does. So this is why you'll see in general, like when we're reporting the descriptive statistics, we're reporting standard deviation, because you can look at a standard deviation and say, okay, for this sample, this is about how far any randomly selected score would fall from the mean. Variance, you take that value and square it. But that's kind of hard to wrap my head around what that means in terms of actual distance. Yeah, Kate, did you have a question? So this is a statistical term, and sort of the reason, like, you don't have to worry about the fancy stuff. It's just if you encounter this in methods articles, this is what it means. Moments are just talk about characteristics of a distribution. So you'll have, we'll talk about this. First is mean, second is your variance, right? Getting central tendency and spread. Then you have skew as third, kurtosis is fourth, looking at sort of different aspects of the shape. So that's just all that is about. Again, we don't need to be like super fancy with this stuff. I just want to let you kind of throw it out there. So if you encounter it, you come like, okay, I understand what they're talking about. Okay, yeah. Direct relationship between variance and standard deviation. Variance is just the square of your standard deviation. Standard deviation, just the square root of your variance. So we'll be doing a lot of moving back and forth between those two things. But what we see with the calculation of variance and standard deviation, if you recall from your undergraduate statistics, the calculation is just a little bit different on whether or not we're talking about population value or a sample value. Okay. Ruin my whole flow here. All right. So if we're talking about calculating standpoint, okay, let's say this this number set of 5 scores. This is my entire population. These are all the individuals in the entire universe I care about. My entire population is composed of these 5 scores. Okay. So what we would do if we wanted to calculate, we would take these scores and we would first calculate a deviation score for each value. Deviation score, we're just going to take the mean and we're going to subtract the mean from every single score. This idea of a deviation value is something that's going to come up again and again and again and again. If I say, if I'm talking about a deviation score, it just means the distance or the difference between whatever that score is and the mean of the distribution. Okay, so we're going to go through, calculate a deviation score. We're going to square each of those deviation scores. Okay, so we're just going to take each one of those deviations. We're going to take it to the power of 2. We're going to square it and have a new column here. Okay. Now what we're going to do is we're going to calculate the sum of squares. Who's heard of sum of squares before? So is that sort of getting back? Yeah. Sum of squares is mysterious, right? Like in undergrad statistics, we always hear about sum of squares back. Boy, what's sum of squares? Sum of squares is just another measure of variability, right? An even less interpretable metric than variance, but it's just the sum of the squared deviation scores, okay? And to calculate my sum of squares, I'm very literally just going to take all of those squared deviation scores, add those up. That's giving me my sum of squares. So why did we go through and square each one of those deviation scores? Seems like an unnecessary step. Why did we do that? Yeah, Allison. Yeah, because why do I need those to be positive values? Yeah. By definition, if I just add up my deviation scores, the answer is 0. right? Has to be mathematically. If it doesn't, you've done something wrong, right? So what we need to do is we need to square these deviation scores to get rid of the negatives. And then what we're going to do is we're going to add those up. This gives us our sum of squares. We'll get into our sum of squares more when we start getting into ANOVAs, right? Sum of squares is just a metric of variability, right? It's not an interpretable or a standard metric of variability. I can't say, Olivia, if I say, hey, like I've got a sum of squares of 5 million, is that a lot or a little? Yeah, I don't know, right? Because there's no way to know exactly what I'm measuring, right? Because it depends on the scaling of what I've got, right? So there's no way to sort of determine it. And so it's not a useful metric in terms of communicating things absent context, but it starts to become critical in calculating our statistics, right? But when you see sum of squares, when we talk about sum of squares, when we get into ANOVA, that should just trigger for you, oh, that's just a measure of variability, okay? So we go through, calculate our sum of squares. And then what we're going to do is we're going to divide that sum of squares by the number of scores in our set or in our population, I guess, to get a variance estimate. Okay. And here for variance, we're using sigma. We're using our Greek letters to indicate our population values. And then if I want to get my population standard deviation, then I just take the square root of that variance to get me my standard deviation. Okay. So again, wanting to work through in a small set so that you can understand and sort of look at they're nowhere and they're not even all that difficult to count. I mean, it's tedious if you've got a bunch of scores, but all we're doing is we're taking our set of scores, we're finding the mean of that, and then we're creating a column of deviation scores. How far are each one of these scores from the mean, squaring those, adding those up, dividing by the number in the population here, and that's giving us our variance, and then we can go through and calculate our standard deviation, okay? So, and if you look at this, and this is one of these things, this isn't a math-heavy course. It might seem like a math-heavy course. Stats can get much, much more math-heavy than sort of what I'm going to have you do, right? But what I want you to do is I don't want any of these statistics that we're working with to feel like they're magical or you don't know where they're coming from. If you go through and take a look and you look at your formula, you can very quickly say, oh, I see what that's representing, right? Here, we're saying that my sum of squares, it's just, oh, this is just all my deviation score, the sum of my square deviation scores, right? When you're looking at these formula, just don't let your eyes gloss. If you're looking at a methods article, someone hit a formula and their eyes just gloss over, you just skip over it. I'll be honest, I do that too, right? Try to avoid that impulse. Look at it, because if you actually, there's the incredible amount of information that comes in to thinking about conceptually what's happening with this stuff. Okay. So this is kind of the definitional formula of how we would go through and calculate variance and standard deviation from a population base. But I can also go through, this is tedious to go through. You can do it easy enough if you got a spreadsheet. Here's computational formula for getting your sum. The same thing as if you do it kind of the definitional way. It's just a mathematical shortcut, okay? So here we're just taking the sum of our squared x values, and I'm subtracting the sum of my x's squared over n. It'll give me the same thing in terms of my sum of squares. Kind of following along in terms of how we go through and calculate those. Okay. All right. One of these things, always, anytime we go through and we calculate anything, first thing you should be thinking about, like, I want to do a plausibility check, like how I have a number, is that number reasonable? Okay. So here, let's see, we've got a distribution of scores here. Mean value for this distribution is 6. I've got, so the closest value to this is 1 unit away, farthest value is 5 units away. What should this tell me about my value for my standard deviation in this set? What do you think, Johnny? Yeah, so I'm calculating standard deviation for this distribution. I've got a mean of 6. I know that sort of at least I've valued my scores is going to fall 1 unit away, at most 5 units away. What does that tell me? What does this start to tell me about my standard deviation? What if I calculate my standard deviation to be 7? Does that work? Yeah, why not? Yeah, it's outside, like, yeah, there, you can't be 7. There's not a single value in my set that's at least 7 units away from the mean, much less that being the average of a randomly selected score, right? So just thinking about having a good conceptual understanding of what our statistics and what our numbers mean start to help us sort of think about, like, is what I have a reasonable value? Because we'll make mistakes. We always make mistakes. And Matt, how, how many hours do you think your average mistake makes when you're running analyses? Yeah, right. And this is the thing, right? So you will make mistakes, and sometimes you'll make a mistake and be like, yikes, that just ate up 2.5 hours of work because I screwed something up. If you can catch those mistakes early as opposed to later, you're going to save yourself a ton of time. Okay. So just thinking about what this means. And again, from sort of one of my favorite papers, sort of Wilkinson, right? Common sense, right? Something that can happen here in SPSS. Sometimes I've got in sort of a set, if I'm using that or whatever program I'm using, I'll go through, and if I have a missing value, I'll hit a 999, because like rarely am I measuring anything where 999 is a real value. But if I forget to tell whatever program I'm using that 999 just indicates that I have a true missing value, and I just calculate that as a score, all my stuff's going to be way out of whack. Hopefully I'm paying enough attention when I look at my descriptives to realize that, whoa, that's not a real value, right? The average score or the average age of my undergraduates certainly isn't 35, right? So what am I going to go through and correct stuff? So always be going through and checking your values to make sure that they're reasonable given what you understand about the stuff. Otherwise, this is the look that I give when I'm reading through problem sets. I'm like, this is very clearly false, right? So just make sure that you're going through and taking a look at that. All right. So if we're thinking about our goal with our inferential statistics is to be going through and trying to understand something about all of our statistics are sort of predicated on this idea that our samples are representative. Are the samples that we collect representative of the types of populations who we're generally interested in inferring things about? Probably not, because a lot of our research is all undergraduates, and there are a lot of ways and reasons why undergraduates are not characteristic of the people who we're probably trying to generalize to, right? But always remember that, so with our statistics, we've set some, and the rules make sense, and the outcomes that we get, so long as we're playing by the rules. But as soon as someone brings, brass knuckles to the boxing match, now all of a sudden sort of the rules have changed, and we sort of can't necessarily sort of depend on those outcomes as being reasonable, right? But if we do have representative samples, right, what we find is that our samples are going to consistently underestimate our population variability, right? Even if I have a perfect randomly selected sample, a randomly drawn sample, what's going to happen when I'm trying to estimate variability is my sample is always going to underestimate that, because what's happening is my extreme scores that are likely out there in my population, I'm not likely to capture those in my sample. And what happens is I'm going to start to get biased because of this. So let's say, again, easy example, let's think about height of undergraduates at the University of Wyoming, right? Let's say I go through and randomly draw students, and let's say a sample of 100, so not a small sample, a decent sized sample. I go through literally all the undergraduates that are enrolled at the University of Wyoming, and I randomly select 100 of them, a better sample than that. And let's say that I do that again and again and again and again. What's going to happen is each one of those samples, assuming height is normally distributed in our sample, my sample is going to mostly be sort of pulled out of the center of that distribution, right? It's just going to, what's going to happen though, is that those people who are very, very small or very, very tall, my sample is probably not going to capture them, right? But these are people out there on the end that are going to increase the variability in my sample, right? They're people, they're undergraduates at the University of Wyoming. They're people who I care about and want to be in my sample, but it's very unlikely that I'm going to systematically capture those individuals just because there's not very many. They're hanging out on the edge of the spectrum. So what's going to happen is my sample is systematically underestimating the variability that's actually out there in the population. Okay. Now, if I have large samples, if I have samples of 1,000, right, I'm much more likely to catch those folks. Small samples, 30, 40, 50, those folks that are sort of above 7 feet or below 5 feet, right? I'm probably, those people who are falling on the tails, I'm probably not going to capture those so much, right? And so what ends up happening is we find that our sample statistics, our estimate of our estimates of variability, variance, and standard deviation as we calculate them based on samples, they're going to be biased, right? They're going to underestimate the variability we have in the sample or in the population. And so this is where we get into sort of understanding sort of biases in our statistics. We say a statistic is biased if the average value over replications is going to systematically or underestimate corresponding population parameter. Okay, in our height example, we would go through and we got everybody, every undergrad at the University of Wyoming measured their height and calculated the variability. My sample statistic is going to be statistically or systematically less than what that is, because on average, those statistics are not going to capture sort of the ends of the distribution. Okay, so I would say I have a biased statistic here. My statistics are unbiased if across replications, the average of my sample statistic across replications is going to be equal to my population parameter. Okay. Now, for here, right, is my mean going to be biased? My sample is sort of given this, if we're talking about height, am I going to have a bias in my sample mean? Hopefully not. Why not? Why, Kate, why might not? Why might I be less worried about my mean value with this than I would be about my variance? Okay. So if my sample is high enough, I'm going to get sort of more representation. But even if I have a small sample, let's say I'm pulling samples at 10, am I going to have a bias? Is my mean going to be, is the calculation of is my sample mean going to be biased? Yeah, yeah. Talk about that, Gabe. Why is, even with small samples? Yeah. Yep. And even if it's not normally distributed, right, it'll still be, it's unbiased, right? It doesn't matter how small the sample is. Now I have to get a lot of samples, but if I'm just grabbing small samples, where are my small samples probably going to, where are the people in my sample going to come from in this distribution? Center. And even if I catch some of these people of my sample and I get a mean that's sort of way far out there, across time with replications, it's still going to pull it in because most of my people are going to be falling in the center. And so the mean is an unbiased population statistic, because everything's kind of there in the middle, and that's where I'm getting people. And so across, if I take the average of all possible samples of size 10 that could be pulled from that distribution, the mean of those means is going to be equal to the population parameter. We'll talk about this in a couple of class periods, okay? But my variability is problematic because in order to capture my full variability, I need to get those people on the ends, and my small samples probably aren't going to get those. My big samples are going to be better, but I'm still going to systematically exclude those people on the end, right? So what we end up having is if we just go through and calculate our sample variance, the same way we calculate our population variance, what we're going to get is a biased statistic. It's going to underestimate the actual population value. This is a consistent bias and we can fix it pretty easily, okay? All we need to do here is we're just going to take the same formula. We're going to sort of calculate our sum of squares the same as we did before, but instead of dividing it by the number of people in our population, like we did with the population parameter, what we're going to do is we're going to take our sum of squares and we're going to divide it by the number of people in our sample minus 1. Okay. What does this do systematically to the calculation of my statistic if I'm dividing that sum of squares by the number of people in my sample minus 1? Yeah. Because I'm dividing by a smaller number, exactly. And Allison, what is the adjustment on that if I have a very small sample? I have a sample of 10. What's the difference? What's the impact if I divide something by 9 instead of 10? Yeah, exactly. If my sample is 500, dividing something by 500 versus not 499 is not going to change anything much. But if I have 10 versus 9, that's going to make a big adjustment. So this is very, very clever and easy way. And sort of mathematically, it turns out if we divide, instead of in our formula, divide our sum of squares by n minus 1 when we're calculating our sample statistic versus the total number of scores in our population as we would if we're with our population parameter, what that's going to do is it's going to give us an adjustment to give us an unbiased statistic of the actual population value. Okay. And we'll see this with a lot of the adjustments that we do. If I've got a really big sample, this isn't going to change anything by any practical, meaningful sense. But if we're working with smaller samples, what this is going to do is give us an unbiased statistic. So if I go through and calculate of all possible samples with replication that I could pull from the population of University of Wyoming undergraduates, if I took the average of all those variance estimates, that average of that variance estimate is going to be equal to the population value, which gives us an unbiased statistic. Okay. So what we need to do when we're thinking about variability is our sample's not capturing those folks on the outside. So what we need to do is make an adjustment in the calculation of our statistic to sort of bump it up a little bit. And so when we do that, that sort of cuts out our bias. Okay. This is one of those things like in undergrad, you probably talked about like, oh, here's the population formula, here's the sample formula, but not really talk about like what that actually is or why that happens. But for you and thinking about research, wanting to understand like this is what's happening, this is why it happens, and why it's important. So again, calculating variance and standard deviation for our sample. Here's our, instead of a population of 5 scores, now we have a sample of 5 scores. Again, still going to calculate our deviation scores, still going to square those deviation scores, still going to sum those square those deviation scores to get our sum of squares. Sum of squares for the sample, sum of squares for the population, same thing, no difference there. Only thing we're going to do now when we're calculating the variance for our sample, we're going to take our sum of squares and we're going to divide it by the number of people in our sample minus 1. And then once we've done that, take the square root of that, gives us our standard deviation, same thing. So the only thing that we're doing different is just changing that denominator just a little bit in the calculation of our variance. Everything else is identical. And again, population or the computational formula for calculating sum of squares is the same as it was for the population because sum of squares is still calculated the same. We're just going through, the only thing that we're adjusting is when we go through and make that adjustment in the calculation of variance. Thumbs up. Cool. All right. So just to recap, we've got sum of squares for our population, our sample, same variance is going to be adjusted. And see here you can see, so we have five scores, right? And our variance for the population, we calculate, if we consider that set of 5 scores, my total population, I get a variance estimate of 8. If I consider that a sample, we get an upward adjustment, right? Because our concern is that we've got a biased statistic that's underestimating, and so we see that jump up a bit if we only are working with 5 scores, okay? Standard deviation, we see corresponding increases there, and then just the final formula to kind of keep that straight in our minds, okay? Here's the thing, rarely, unless you're told otherwise, you're almost always going to be using the sample statistics because we never are working with populations, right? So just keep that in mind, but want you to know conceptually and thinking about variability as a construct and what it means, kind of why we're making that adjustment in the calculation of our statistics. All right. So a lot about variance, standard deviation. Again, thinking about this is telling us in general the typical distance from the mean of any randomly selected score from the distribution. In any distribution, some people are going to be close to mean, other people are going to be farther away from the mean. Standard deviation just tells us on average sort of where a randomly selected score is likely to fall. Again, thinking about if I know both the mean and standard deviation of a distribution with that information, I know kind of generally how distributed these scores are likely to be. If I were to pull a randomly selected score, if I know the mean and standard deviation, I go know sort of about where any score is likely to occur if I were to go through and pull something. It also helps me say something about and draw some inferences from an individual score, right? If we have some construct that falls on a normal curve, we know that sort of points on that normal curve in terms of distance start to correspond to sort of percentiles in the larger population, right? So this starts to become important. I think for clinical people, if I say, here's client score on measure X, does that tell me anything about anything? Not really. But if I say, here's client score on measure X, clinical population has an average of this with a standard deviation of this, if we assume that there's some sort of normal distribution of that, now all of a sudden I can say, oh, is this person a couple standard deviations above the mean? This is a very extreme value or not extreme value, or this is typical, not typical, right? Same thing for experimental folks. If you have like some sort of manipulation or something like that, and you're saying from a previous paper, we expect average of people from just sort of who experience this manipulation report scores about here. Here's the standard deviation. If I go through and run, let's say, you know, this other study was conducted in, say, a different country or something along those lines, and I go through and take a look at it, I can say, am I getting about where within what's would be expected based on this, or is there maybe something different going on with this manipulation in the population that I'm pulling from, right? So thinking about that helps us draw some interpretations about how extreme or how representative our data are relative to other people, okay? And this is kind of the heart and soul of inferential statistics. We'll get more into this as we sort of move on with stuff. Okay. So if we're thinking about this, let's say in the US, average height of adult males is about 5'10" with a standard deviation of 3. Okay. So I've got David. David's 5'6". What can I infer about David's height relative to sort of the average? What's that? Uh-huh. Yeah. Yeah. So we would say that David is, so if the standard deviation is 3, standard deviation below is going to be 5'7". So David's hanging out just a little under a standard deviation, right? So is David shorter? Certainly. Is David inordinately short? Probably not, right? But on the lower end of the distribution. What about, we'll say John is 6'6". What about that? Yeah. Yeah, that's pretty tall. We've got someone who's, what's that, Gabe? Yeah, we're looking at, yeah, close to 3 standard deviations, right? That's on the high end of that spectrum, right? So we've got someone who is inordinately tall there, right? Matthew's 5'2". We would probably say that that's quite shorter than to the average person, right? So we can go through and eyeball that and say, oh yeah, that's a tall guy, that's a short guy, right? But if we're going through and we have this information, we can start to quantify the extent to which this is extreme. And if we know that distribution, we can start to actually put them in percentiles and sort of say like, yes, this person is sort of probably about sort of X% taller than sort of X or it's taller than sort of X% of sort of the general population, things along those lines. So just knowing just means and standard deviation to help us put more make more specific inferences about sort of where scores are likely to fall. Okay. So this is easy to go through and take a look because I can look at these scores back. Oh yeah, that's a tall guy. That's a short guy, because height has intrinsic meaning to us, right? We sort of understand we live in a world where this makes sense. But what happens if we switch over and start using constructs that have no intrinsic meaning, right? It's an extroversion score that I've created, right? I can say, hey, a score on this is 75. Does that mean anything? I don't know, because I don't know anything about it. This is not measuring anything real. It's a hypothetical construct, right? But if I know from a big norming sample what the mean and standard deviation are, now all of a sudden I can take that and start attaching meaning to that, right? So we've got Bert has a score of 120. Where is Bert at, Danielle, in terms of level of extroversion? Yeah, right. And if we see someone's a standard deviation and a half above the mean, that's decently high, right? So is it way out of bounds? Not really, but it's still pretty high, right? So I can infer that if this is a valid measure, that Bert's a pretty extroverted, outgoing guy, right? Leon, 125, right? That's super high. Reynolds, 55, that's way down, right? So with this information, if you just look at these scores, they don't have any meaning, right? Until I throw a mean and a standard deviation up. And now all of a sudden I can place this person relative to sort of a population that I can sort of reference. All right. So when we're looking at our inferential statistics, our goal is we're trying to sort of separate signal from noise, okay? The question that we're trying to address here is, are the differences that we're seeing, or the patterns that we're seeing, are these things real things that maybe reflect sort of what's actually happening out there in the universe, or is this just random stuff that happens just because random stuff is going to happen? Okay. Now, if we're talking about our means-based analyses, if I've got low variability in the data, it's pretty easy to see differences, right? As my variability starts to get high, it starts to obscure things, and it becomes much more difficult to go through and actually detect some of these patterns, stuff that you would otherwise maybe just be able to eyeball. Okay. So let's say we've got experiment A and experiment B. Look at experiment A, we've got values for group 1 and values for group 2. Experiment B, values for group A, values for group B. Okay. And which one of these, experiment A or experiment B, which one of these would you say is more clearly identifying differences across the two groups? Or is it easier to see the differences? Experiment B. So yeah, what's your thinking on that? What about the within group variability? Do we have more or less variability within group variability? Variability within groups. Whereas experiment A, my groups are pretty tightly connected together, right? So I have some sort of higher and that range, right? Which is a good thing to take a look at, but it's kind of hard to start to see kind of where those differences are. If I take the means of all through group 1 and group 2, group A and group B, the means are identical across these, right? But what we've got is much more variability across these sets, right? And so if I take a look at group A, my low variability, got one group with a mean of 35 and another group with a mean of 40. Looking at that in this data, yeah, I've got two distributions that almost have no overlap, right? And that, what we got, that 5-point difference is very, very easy to see in this low variability scenario. Okay. What about that? Much harder to see, right? The mean difference is still 5. Like the average difference across my groups is um, the exact same. But what I've done here is I've blown up my variability. Now all of a sudden it's very difficult. If I go through and I take a look at the distribution curves that I've superimposed on there, you can kind of see. But if I'm just looking at that bar graph, hard to say if there's much more, even though the average difference across these groups is the same, much more difficult to detect the difference in that second experiment as opposed to the first experiment. With this experiment, we're going to need a whole lot of people in that sample in order to detect that difference relative to this. This is going to be pretty clear. Our effect size here is going to be much larger, even though the absolute difference is the same. Effect size here is going to be much larger because we got much less variability as opposed to this. Okay, so when I'm talking about signal to noise, this is where, particularly for a means-based analyses, as we start to get more static in there and say, okay, this is my mean, this is my best middle guess, but so the variability I get in that set starts to become more. And so this is where, Mandy, going back to your question, talking about error, if the only thing that impacted values was what group I'm in, right? This is pretty good. I've got 35, 34, 30, not a lot of error in here because everybody's really kind of tightly packed. Here, versus that. And so thinking about error and variability in terms of, you're kind of seeing that as a visual as to what's going on with some of this stuff. All right. So characteristics of my standard deviation. Add, subtract a constant from a score doesn't change my standard deviation. If I subtract a score of 2 from every score and value in the distribution, it switches the mean down, but the variability is the same, doesn't change anything. If I multiply, divide every score by a constant, it's going to cause the standard deviation to change by the same factor, right? So if I have a mean of 48 in inches and a standard deviation of 12, right? And I change those inches into feet, what's my new mean? Yeah, so I measured something in inches, right? And so the mean is 48, the standard deviation is 12. But I go through and recalculate those. I divide everything by 12 to change everything to feet. What's my new mean going to be in that scenario? 4. And what's my standard deviation going to be? 1, right? So I'm going through and I'm dividing everything by a constant. It just changes everything by a constant. So things that start to influence my variability, okay? Extreme scores, my range, my variance, my standard deviation. If I have extreme values, it's going to really impact all of that stuff, right? So this is where we want to go through in our screening and start to take a look. Do we have folks who are way out there on the margins, particularly if I'm working with small samples that are going to start to blow up my metrics of variability as I've calculated them for the sample. Sample size, range increases with sample size, but my variance and my standard deviation stay pretty stable. Why does this make sense? I think, Mesa. Yeah, so we know that sample size will increase my range, but it's not going to impact my variance or my standard deviation all that much. What's that now? Oh, no, increasing my sample size. So the number of people in my sample size gets bigger. What am I more likely to do if I'm thinking about variability? Increasing my sort of my range, right? I'm sort of getting, I'm more likely to capture. So that as my sample size gets bigger, I'm going to start to increase my opportunity to catch those people who are below 5 feet as an adult or above, taller than me, in terms of things. So my range is going to get bigger. But my variance and my standard deviation are going to stay relatively stable. Why is that going to happen? What's this, Johnny? Yeah, yeah, because we went through and we're applying a correction for those small as my sample gets larger, the sort of upward correction on that starts to get smaller, right? If I've got a small sample, it gets bigger, right? And so it's kind of you can think of it as an adaptive correction for that. So as my sample sizes get larger and larger, my estimate of the variance is going to stay the same across that. Okay. Stability under sampling range, all over the place, right? Because it's based on two scores. It's the low score and the high score. Range across replications can jump all over the place. But again, my variance, my standard deviation are going to stay pretty stable with things, okay? Limitation with open-ended distributions, again, censored variables. I can't calculate range. I can't calculate variance or standard deviation with censored data because I don't have actual values to go through and calculate, right? There are specialized statistical models that account for censored data, but one of those things that you always want to be careful in thinking about in terms of the planning component of your studies. What am I wanting to measure? How am I going to measure this? And what are the implications for analyses, right? It's easy to say like, oh, this or above, right? But if I do that, I'm really kind of handicapping myself in terms of what I can actually do without sort of having to make some serious consideration, limitations in terms of sort of the actual scores that I can get and sort of identifying aspects of my sample. All right. Questions about this? Okay, cool. Other thing we want to do, so we talked about the middle value. We talked about the variability in my sample. We also want to be thinking about the shape of my distribution. Here we've got a symmetrical distribution, but identify this as a normal distribution, right? And here we're seeing mean, median, mode all be in the same spot. We've got this nice bell-shaped curve. Everything's nice, right, in the world. This is what we sort of really enjoy, right? But we can also have non-normal, we can have symmetrical distributions that are non-normal. Symmetrical just means if I cut it down the middle and fold it in half, I get the same thing, right? I can have bimodal, multimodal distributions that are symmetrical, but they're not normal, right? So thinking about how we're describing distributions and things along those lines in ways that are sort of communicating what's actually happening in our data. Yeah. You can also have symmetrical non-normal data that look like this, right? This is certainly symmetrical, but it's for sure not normal, right? Here we've got a square distribution where we've got even representation across all of these, right? So thinking about these as terms to start to use as you're working through screenings, when I'm asking you to describe sort of what your data look like, it's actually kind of tricky. Like, okay, like how do I describe this? So symmetrical is a good way to sort of talk about this, but I could say, symmetrical but bimodal here, right? Here I could say is a square distribution, symmetrical square distribution, something along those lines. It's just terms to start to communicate what's happening in your data. Okay? Other thing that we can have, even with non-symmetrical, when we have non-symmetrical data, we can start to get into skewed distributions, okay? Skew describes the symmetry. We can have positive skew, negative skew. Positive skew is always defined by the tail. Does the tail stretch out towards positive values? If so, it's a positive distribution. If the tail stretches out towards lower values, we've got a negative skew, okay? This is going to be sometimes what people get turned around with is we're not worried about the body of the distribution. We're worried about where the tail is going here, okay? Also skew as the third population moment. So Kate, this is sort of just the next characteristic that we would talk about. A skewed distribution gives us information about the symmetry. The thing to remember again is that if we have a skewed distribution, the mean is no longer necessarily as representative measure of central tendency in the skew distribution. Now, we're always going to have some skew, right? And so this is where we want to start thinking about like how much skew do we have? If I have any skew, it doesn't mean that mean's not good. It just means that it's it becomes less representative as that skew starts to increase. Okay. And again, what we can see with a classic skew distribution, the mean is always going to be drug out farther towards the tail. Okay. The mode is always going to be right there at the body of the distribution, and the median is going to be in between those 2 points, right? Which is why we would typically identify the median as technically the best measure of central tendency for a skewed distribution. Questions about skew? Kurtosis. Okay, people generally good with mean variability, although sort of conceptually variability can get tricky. Skew, then we get into kurtosis, right? If anybody's interested, I have a wonderful paper, like a whole paper on kurtosis. If you want to read, if you need some evening reading and you just want to read about kurtosis, it's not right before you go to bed because then you'll be awake with excitement. Thinking about kurtosis, this is our fourth population moment, describes the shoulders and the peaks of our distribution. We've got positive kurtosis. This is a distribution, heavier tails, narrow peak. Okay. We've got a kind of a skinny peak on the top, and then in the classic distribution, what happens is we get kind of these flattened tails that extend out. If we've got negative kurtosis, we talk about this as a platykurtic distribution. We've got a flattened center and heavy shoulders, kind of a mounded shape here. Okay. What my wonderful paper on kurtosis works through is that oftentimes, if you look at textbooks, somehow, some point along the way, someone got it wrong, and then people kept copying the people who got it wrong and putting it in textbooks. And we'll talk about like kurtotic, negative kurtosis as having tails that kind of go up. It's not. It's sort of a domed shape versus kind of this peaked shape here. In terms of looking at the shape of this distribution. Okay. What's that? Okay. Does Hal get it wrong? Oh, yeah, we'll go through it and take a look at it. But in terms of thinking about the distribution, right? Things that can happen with underestimate our population variance. Okay. If I get a kurtotic distribution, my concern is that the statistics that I calculate from this kurtotic distribution are going to underestimate my population variance. Okay. Now it seems pretty clear for my negative kurtosis why I'm going to underestimate, right? Because I'm not getting any of those tails, right? So of course I'm going to underestimate my population variability if I've got a platykurtic distribution. Like, why am I underestimating variability? Because those flat tails kind of go out there. What's contributing to the underestimation of population variability in my positive kurtosis? Yeah, you're right. I'm giving up one thing for the other, right? I'm getting more stuff out here, but down here in the bulk of the distribution where I should be getting more variability, I'm not. I'm getting a peak thing. So I'm missing the middle piece of things, which is going to underestimate my variability. I'm sort of making up for it out here, but I'm losing it in the middle. Down here, I'm losing the tails, or I'm sort of overestimating here, but I'm losing the tails. So the concern with anytime you have a kurtotic distribution is that the concern is that I'm have the potential to systematically underestimate the actual population variability if I'm working with this stuff. Okay. So if I'm doing this, it's going to impact the quality of variance tests. It's going to contribute to bias in my parameter estimates, my standard errors. As we get into this, we'll see the standard error. Your variability is critical in calculating your standard error. And if your standard error is in the bottom of your test statistic, then the bottom is too small. And then that inflates my test statistics and things along these lines. So the concern is if I've got something that isn't representative, then what's going to happen is I'm going to underestimate. People comfortable in terms of our different sort of kurtosis values, kind of what's happening with this? So very kurtotic, wholly kurtotic. Sort of that has no tails, and it's all sort of flat, right? So this would be, if you were to calculate a kurtosis value with this, it would be probably pretty high. And this is oftentimes what we'll see if we see high kurtosis. It's you get kind of this square distribution, which can be problematic depending on what you're trying to do with stuff. All right. Yeah. No peak in it, right? Positive kurtosis, I'm going to have kind of a skinny peak, and then things kind of flatten out like that. Skew and kurtosis. We can go through calculus for skew and kurtosis, and we can test to see if we find significant skew and kurtosis. The problem is that right? As size increases, what happens to the power of my test? Goes up, right? And if I've got a really powerful test, what happens? I can start to detect deviations that are pretty small, right? So if I got a sample of 200 people and I test to see whether or not I have significant kurtosis or significant skew, what's the answer going to be? Probably, right? But all that does is just tells me my skew or kurtosis value isn't zero, and that's not what the assumption of my test is. And so, in general, the significance tests for skew or kurtosis are not useful for anything really. Shape of the distribution, looking at what our actual graphs are looking like, and the absolute value of these metrics are going to be more informative in trying to determine whether or not I have a problem or not. Generally, we think about skew kurtosis values of less than 2 is kind of our general rule of thumb. Is this sort of a lot or a little? Okay. Important when we're saying, one of the things that'll happen is someone will say like, oh, I'm going through a screening and I've got a skew value of 1.8, but that's less than 2, that my distribution is approximately normal. Now, like if you see a skew of 1.8, it's going to be very clearly skewed. It doesn't mean it's approximately normal. We're just saying, trying to identify, like, do we have problematic deviations from normality in these data? So just being careful about the words that we use to describe things starts to communicate information that may or may not be accurate. So thinking about these violations as occurring on a continuum. Rarely in this class will I ever say, here's the hard and fast set in stone rule. If you're above it, you're bad. If you're below it, you're good, type of thing. Everything we're talking about is on a continuum of evidence, a continuum of probability. We have benchmarks that we kind of use so that we can kind of speak the same language in terms of stuff, but rarely, if ever, is there going to be a case where here's the bright line, yeah, go, no go decisions if we're thinking carefully about things. Okay. So, depending on the types of analyses that we're doing, characteristics of the sample, sometimes high values can be problematic. We got sort of skew less than 2, kurtosis less than 8. Talking about that is sort of we can make that argument in some sort of circumstances. It's kind of stretching it, but just to give you a sense for that, there's not one universal sort of standard that's been handed down from the sky this is the thing, right? It's taking into context, what am I trying to do? What's the size of my sample? Sort of, is this consistent with what I would expect from these data, and sort of making judgment calls based on that. Okay. Yeah. I mean, that's nice if it is, but if it's not, and sort of this is what happens is people will sort of learn sort of those rules and take them as gospel, and then start doing weird stuff with their data that they don't need to be doing, right? Yeah, yeah. We'll get into sort of why that's problematic. So what we want to do is understand, like, what are the actual assumptions of my test, And like, is this gonna fool with stuff? To what extent will it? And sort of the answer is never yes, no. We like yes, no answers because they're easy. But when we're actually doing this sort of in training, sort of where you all are at, like the answer is rarely, if ever, yes, no. It's to what extent is this? And so if I go through and do this, sort of to what extent is this putting limitations on sort of the type of inference that I can have? And a lot of times our tests are pretty robust and like, yeah, it actually probably isn't gonna make any difference, right? So just wanting to go through, and that's why we're gonna spend some time so you can start to make decisions based on your project, what you're trying to do. Is this problematic or is it not? Question. Other questions? All right. Yeah. So, and sort of the issue with skew and kurtosis, as my samples start to get increasingly large, stuff starts to go away, and we'll talk about why that is. But again, like, if the question is like, how sample do I need? Is as big as you can get it. Like, sort of whatever your resources are, I would go for that because it's going to increase. So it starts to make your data much more robust to the types of things that can go wrong. And so large samples generally will help out in terms of identifying effects, accounting for sort of weird stuff here. So yeah. So again, this is just another thing so if you're saying, oh, if it's less than 1 or positive 1, then I'm okay. If it's not, like, oh, well, I don't know, how big is your sample? Like, what are you trying to do? Like, all of that starts to factor into making a determination on whether or not it's going to be a problematic or not. All right. So yeah, do not in any sort of situation ever say like, because this is above or below a benchmark, then it's fine or it's not fine. I'll flag you on that, right? Talk to me about sort of, is this something that should be concerning or should people be concerned about? In a lot of the screenings, you've got again, a paper that talks about statistical consulting and sort of thinking about that. When we're working through our screening, I want you to be thinking about like playing the role as statistical consultant. Am I communicating to my client? Is this something to be concerned about or not? Or sort of what limitations this put on interpretation, and thinking about things in degree as opposed to kind, because that locks us into, gives us much more flexibility and keeps us out of yes, no decisions, right? Answer is always, it depends. Oh, there's Tara. There's if you use bright line things, Tara will sort of, she likes it when I put pictures of her in my lecture slides. It's her favorite. Think about outliers, extreme values. Univariate outlier, these are going to be extreme values in some sort of distribution. Okay. Causes we might end up with extreme values, incorrect data entry. Sometimes you can have shiftless undergrad RAs who just are entering things inappropriately, and not paying attention to their data entry. So always want to go through and check to see, hey, if I got a weird score, is this actually a weird score? Is it something that was entered not right? Have I failed to specify missing data codes in my data, right? I put in 999 so that I know that's just not a missing value in the set. Because if I just see a missing value, I don't know if is that for real missing, or did someone just forget to enter it, or what happened, right? To get some sort of code in there that sort of tells the program, hey, this means it's missing. But if I forget to tell the program to tell me that that's missing, then I can read it as an actual number. Cases in a member of the intended population of study. Okay. Let's say that I'm interested in looking at, in undergraduates, I'm interested in looking at income, because I'm looking at sort of what are sort of economic resources for undergraduates and things along those lines. And so I've got sort of my distribution, and then I've got someone who's reporting making 6 figures as an undergraduate. I'm like, yikes, what's going on? And I find it's sort of someone from the community taking a class who's an established professional, who's quite well, better than me, sort of going through. Is this someone who I'm interested in looking at? Probably not. This is an outlier because they're not part of my population of interest, which is, 18 to 22-year-olds, and kind of what's going on there. And so if that's the case, that's easy. Kick that person out because they're not relevant, right? But sometimes I might have sort of the person is a member of the intended population, but they're just variability is underestimated in the sample, right? I may be going through again the height example because it's easy. Maybe I truly am interested in sort of growth development, things along those lines, and sort of in adolescents and emerging adults, and I'm interested in height and weight or something along the nutrition, and maybe I get someone who's just very large, right? We got someone who's say 7 foot tall, 280 pounds, right? That's going to be an outlier in my data, right? They're not representative of the people I want to get. It's just my sample. There's probably, I missed all the people in between, sort of the other end of the distribution and that person, and they're kind of hanging out there. What I need to do then is think about, like, what do I do with this case? How do I go through and handle it? Okay. But the consequences of outliers or extreme values is all over the place, right? It's hard to predict what that's going to do. These can have cases that have undue influence on my coefficients, right? Sort of my means, my variances, and things along those lines. They can start dragging those all over the place. I can have inflation of type 1 error, inflation of type 2 error. I can have a solution that doesn't generalize to anything because it's been pulled out of whack by this case or a handful of cases. Really, really unpredictable. I can't say, like, oh, I have some extreme values. What's the impact that this is going to have on my analyses? I don't know. That's a grab bag. That's a wild card in terms of stuff, right? So wanting to be very, very careful. The good news is that for the types of things we tend to study and measure, less of an issue with this, but still something you go through and take a look at. All right. Thinking about outliers in categorical data, okay? We don't think about this so much. We think about outliers as occurring on that continuous variable, right? But we can also have outliers in categorical data. If I have dichotomous variables that have uneven splits, about 9-to-1, right? We can talk about this as being a categorical outlier, okay? What happens is whoever the cases in that smaller group start to have an undue impact on my model, right? They have an outsized impact. These extreme splits can start to attenuate associations with other variables. Like if I had sort of equal representation, I would see an effect, but because I don't, it's masking that. I'm not seeing it. And so what we want to do is think about, if we have this situation, want to think about, like, is this a critical variable to include in my analyses? Or does including this into my analyses mess stuff up, right? And in psychological research, working with undergraduate students, our samples are inordinately white and inordinately female, right? And sometimes, I might want to look at sort of diversity aspects in my sample, but if that's what I want to do, I really need to make sure that I'm doing something to go through and make sure that I'm sort of capturing, so whatever diverse population it is, I'm trying to capture, because otherwise what's going to happen is I'm going to have something that's not representative. And if I try and plug it into my analysis, it's going to sort of throw things off, right? So wanting to think carefully, again, on the planning stage, if this is something that's critical and important for your study, making sure that you're doing everything you can to get representation there. And thinking, but if it's not, if it's kind of exploratory, sort of considering the possibility that if I throw something in there, I might say, oh, this doesn't make a difference, or I don't have evidence this makes a difference, when in fact it does. I just didn't capture enough people to go through and sort of identify the effect that it might have. Or it's something that actually doesn't generalize to anybody because I haven't met the requirements in my, or the assumptions of my analyses, okay? So wanting to think about extreme values is not just occurring on a continuum of our continuous, but that's general where we're thinking, but even with our categorical variables, making sure that we have sort of splits that aren't sort of ridiculously different. Our extreme values with our continuous data, we can go through and calculate these as z-scores. Again, sometimes being a general rule of thumb is 3.29. 3.3 is sort of our benchmark for, like, oh, hey, this is something we might call an extreme score, which is just giving us units of standard deviation away from the mean. This is a good way, this is a good thing to do, and we will do this because it helps us put, if Abby tells me that she's got an extreme value in her set, I don't know what that means. Abby might have a very different definition of what's an extreme value than I do. But if we can put a z-score on it, that tells me sort of objectively how far that score is from the mean. But what we don't want to do is just say, oh, this score has a z-score value of 3.3, therefore it's an outlier, and I'm going to throw it out of my study. Nope, 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 nope. Right? We're using this to qualify characteristics, not making yes/no decisions on stuff. Okay. So this is why we always want to get graphical representation, because if we got really, really large samples, I'm always going to have extreme scores. That's the whole idea of a large sample, is trying to get those people on the outside, right? But if I got a really large sample, does it matter if I have people on the outside? Are those going to fool with my sort of estimates? Probably not, because I'm going to have people sort of toward the middle that sort of start to moderate that, right? So again, what we want to do over the course of the semester is make careful and intentional decisions about what we're doing with our data and the extent to which things are problematic versus not, as opposed to just making yes/no decisions on whether or not I should keep something or not keep something. Yeah. All right. Going through graphing things, okay. We got bar graphs. These are nice for presenting frequencies and categorical data, mean differences across experimental conditions, right? A nice bar graph sort of pop that up. We can kind of say, oh, here's the representation of different groups within our data, can be useful. Histograms. Here we're looking at continuous distributions with our histograms. Mode, kurtosis, right? Histograms are nice ways of representing the full range of our scores, right? And sort of looking at what those actual scores are, how do they fall out, right? So you'll be running a lot of histograms this semester. Histograms are nice, right? We can see, so here we've got some PTSD scores. You can see this is sort of relatively symmetrical. We've got a little bit of a negative skew, which we can kind of see. Got a little bit of negative kurtosis, which is saying kind of a peaked negative kurtosis, which kind of we don't have any real tails on this distribution. Mean, median, and mode, all pretty close, particularly given the range of these scores, right? So not too bad. Contrast this with our other graph here. Here, our mean, median, mode are all about pretty close, right? But we've got a very, very different distribution. Here we've got a very clear skew, 2.4. Our kurtosis is 6, right? So we've got a really narrow distribution here. So I can go through and I can just give you those. I can give you these numbers, but it doesn't give you a good sense of what that data actually looks like. The histogram is not a nice way to visualize what's going on in the full set of scores. Okay. The downside of your histogram is your histogram is going to be different depending on how you construct it, right? I can start screwing around with the binning of those values into how many values or what cases go into certain bars, and start changing the shape and sort of the look of that distribution. So in SPSS has some defaults that we'll just go through and does a pretty good job, right? But I think Johnny's going to be working with Stata, which is what we use in our lab to go through and do stuff. Stata defaults, I like it less. It's easy to go through and sort of specify exactly what happens, but if somewhat problematic, if I create a histogram in this program and I create a histogram in this program and the picture looks completely different, right? Sort of starts to speak to, well, the shape of that distribution starts to change. These won't change, the numbers won't change, but the picture starts to change depending on how I go through and bin things, okay? And so that's the real limitation of the histogram. So what we have instead is we have box plots at our disposal, okay? Box plots, there are rules to creating a box plot, and those rules are the same, functionally the same across sort of programs, right? And what it starts to tell us is some of these median-based statistics. So if we got a box plot right here, our midline, this is our median. That's our 50th percentile. At that line, half of scores fall above the line, other half of scores fall below the line. It's the same every single time, okay? We've got our bounds of the box. This corresponds to our first and our third quartile, okay? 25th percentile, 75th percentile. and our box covers our interquartile range, our middle 50, right? So half of the scores in this distribution are falling here, half of them are falling here. Same with every time you calculate these. Our whiskers, okay? These talked about is the inner fence. This can correspond to two things. It's either capturing the minimum and maximum values in that distribution, or it's capturing the maximum or the most extreme value that's still within 1.5 times the interquartile range. So here's the interquartile range, right? This top and bottom, our whiskers or our fence, it's either capturing the min or max or the most extreme scores that are still 1.5 times sort of the interquartile range, sort of from there. Interquartile range is the boundary of your box. So this is the interquartile range. So 1.5 times the interquartile range. So it's either the min or the max or sort of outside the interquartile range. So here, what we're seeing is this is the min value, max value, min value, max value of these. So it's pretty straightforward. Okay. Extreme values, though, these are going to be identified as individual points that extend beyond the whiskers. Okay. So if I've got points that extend out beyond the whiskers, these are values that are either going to be 1.5 times the interquartile range from the distribution. If I get asterisks in SPSS, asterisks, you'll see open dots for values that are 1.5 times the interquartile range out there. Asterisks are ones that are 3 times the interquartile, over 3 times the interquartile range, right? And so what we can start to do with these box plots is start talking about very specific characteristics of our data in terms of median-based statistics. So if I've got normally distributed data, about 95% of our scores should fall between the whiskers of my box plot, okay? Assuming I have a normal distribution, okay? If I've got stuff, a normal distribution, a nice symmetrical box plot, things that are falling out of there are sort of starting to become sort of more extreme values, okay? So if I'm looking at this plot here, if I'm looking at pre-post scores, I'm saying at pre-test, I've got a pretty nice symmetrical distribution here. Everything's it's about the same above the median, below the median, looking pretty good. By the time we get to post, I've got a sure shift in median values, right? So we're seeing a shift in median, but I'm starting to get an imbalance, right? Anybody sort of give me an idea of what that distribution might look like if we plotted it? So everything's kind of bunched up. Sort of my middle value is right here, my median, and then things are going to be becoming start towards the positive. What about this? What's happening here? Dylan, what do you think? What are we seeing here with this example? In terms of the shape of these 4 conditions. Can someone give her a hand? Yeah. Yeah, it's a little bit taller. Is it too much taller? Okay. The midline's pretty good. Yeah, what do you think, Debbie? Yeah, yeah. Right. So we've got these are pretty good, right? Not too bad, right? Fairly relatively balanced. Yeah, there's a little drift towards this end or drift towards that end, but not too much. And so for conditions 1, 2, 3, we got the ends of the whiskers being the most extreme and the least, or the sort of 2 extreme values on the low end and the high end. What's going on in condition 4? What are we seeing here? Yeah. Okay, I would say two extreme values with this, right? And so what do what are the bounds what do those whiskers then correspond to in condition 4? So what does the bounds of that whisker correspond to? Okay, close, right? So 1.5 times the interquartile range. What's that now? Yep. So it's not min or max. Okay. Yep. So those bounds are going to be in this distribution, the values, the most extreme value that's still within 1.5 times the interquartile range. That's where that whisker is marked. And the same thing, the low value, the lowest value in the set that's still within 1.5 times the interquartile range. That's where those are. And then data points up beyond that are going to be indicated with the circles. Okay. So still a relatively symmetrical distribution overall. We do have some larger scores going on right here, right? What? Yeah.
Like outliers
Interchange. Like, so this is my personal preference.
Okay.
Outliers sounds like a categorical thing. Like I'm either an outlier or I'm not, right? And then sort of people, it sort of gets people falling into yes or no thinking. Extreme values, I just because extreme, well, how extreme, right? Like, and so I don't necessarily like I'm not going to ding you, but I just wanted sort of starting to thinking about these as extreme values, because if I just sort of label something as a category or as an outlier, categorically, I think, oh, that's bad or that's far away. Well, it kind of depends on a lot of different things. Yeah.
So
Uh-huh.
you're right. So
Yeah. And so this is where we start getting into semantic issues with what's an outlier, what's an extreme value, and things along those. What SPSS does is a value. So good example. So these open dots, these are values that in the data set that are falling beyond 1.5 times the interquartile range from the median. Okay. Or from, yes, this from your 75th percentile. Here we've got something that's more than three times the interquartile range. So it's giving you a degree of severity. But what's nice about box plots is very specifically what they're using as their definition for asterisks versus open circles and things like that, right? So if we're looking at this, what we see is some very skewed distribution here across this, right? So where most people are pretty low, but we've got a clear skewed distribution up. And so what we can start to do is start attaching specific information to these values based on median-based statistics. Yeah. So it just kind of depends, right? So that what it's telling you is the dark line, right, is telling you the median of each one of those, right? The lower bounds of the box is the first quartile, the upper is the third quartile, and then everything we get beyond that starts to become increasingly extreme values, right? And so what's nice about the box plot relative to the histogram, if we were to go through and plot these all out, we could see then we get the kind of the full range. But the problem is, depending on how SPSS has decided to bin that, it starts to look a little bit different in terms of things. The thing with the box plot is the rules of putting it together are the same and constant, so we can kind of identify all those as consistent across things. So again, they're just different ways of looking at the data and sort of and communicating things. Yeah. Yeah. So these here, like, sort of none of this is a normal curve, right? Is gonna be this, right? And so what we want to do is we could go through different ways we can represent this. We can represent this as histograms, right? And go through and see that, yes, we've got out there, but just looking at that histogram, that doesn't give how far out that is. I mean, it gives me a nice visual representation. The box plot, I can go through and say, here's my median values, 1.5 times the inner quartile, or beyond 1.5 times the inner quartile range. Here's the value, still within 1.5, beyond 3 times the inner quartile range. Yes, yeah. Okay. If you have other questions, so to go through, last slide, just final thoughts, so just general things that are serious and funny. Sort of working through this, want to start just with some basic foundation stuff like that. We'll jump into like Z-score stuff like that next class and start thinking about kind of how all that stuff falls out. But excellent questions. We're at time and I don't want to keep you. So go ahead and take off. But if you have questions about this, let me know. Other people can hang out. Other people can hang out and ask me questions if you have questions. Yes. All right. Yeah, Johnny. Yeah. Kurtosis, it kind of depends, right? I mean, like if you go through and you transform, it'll start to reduce your values of kurtosis and get things a little bit more. But again, it depends on what you're trying to do, right? If I'm doing means-based analyses and I've got quite a bit of kurtosis, but it's just because I kind of got a square distribution in my set, I'm probably not gonna be too worried about that, right? But if I'm trying to sort of give an estimate for like, oh, based on my sample, this is sort of my best estimate of the variability in the population, then I might be more concerned about that because I'm probably underestimating that given the distribution. So yeah, we'll go through and talk about some of that screening and when things start to become problems and when they don't. And a lot of that is based on sort of our assumptions of our tests. So awesome. Yeah. Manny, does this, you kind of get with or here, hold up. So. Oh no, I'm just shutting down the video here.